So I'm going to talk to you very briefly about how we can use visual data to model people's preferences. In other words, how we can understand the visual dimensions that guide people's purchases and preferences. And of course, in addition to modeling the preferences themselves from visual data, we also want to understand the temporal dynamics of preferences. In other words, how do people's preferences towards visual signals change over time? So I think these are the two components you would need to model what we would really consider to be fashion, right? It's not just how do individuals or communities respond to different visual stimuli when selecting things like clothing, but it's also what are the visual stimuli that people respond to right now? How are those things changing over time? What's going to be popular tomorrow, and how does that differ from the 90s, and so on and so forth. And we're going to do this in terms of these very popular visual features that I'm sure you've seen a lot of, like visual features extracted from CNNs. So we're going to be very agnostic as to what kind of visual features fashion actually means. These are going to describe all kinds of things like texture and color and pattern and fabric and size, who knows? And we don't know which of those describe fashion, but that's what we're going to try and learn from data. And we'll try and do this on the Amazon corpus of products, which contains something like nearly 10 million products, 20 million users, and more importantly, 140 million interactions between products and users. That includes a star rating and a review. What we're really interested in is simply the binary feedback here that a user chose to purchase a product versus ones that they did not purchase. And most importantly, we have for each product the image associated with it. So we studied this data for all Amazon products, but here we're mainly concerned with men's and women's clothing, which accounts for something like a third to a half of this corpus. Okay, so the basic problem setup is something like this. We're given a user and an item. And don't worry about the timestamp just yet, but that'll come into it. And maybe we'd like to estimate something like a star rating, or for the case of predicting what people will purchase, maybe we want to estimate just true or false. Would they purchase it or not? Or even perhaps something like a probability, a number between something in the range 0 to 1, which would say how likely are they to purchase it. And that's not quite a recommender system, but it's kind of the black box that you'd build a recommender system from. It says, if I were to suggest this item to a user, maybe at a particular point in time, what is the probability that they would interact positively with it, say by purchasing it? And we can use that to rank probable actions that a user would take. So this is a very standard type of problem in recommender systems. The way this is traditionally addressed, ignoring things like visual signals for the moment, is to find things like low-dimensional representations of people's preferences and items' properties. So this could be a vector describing, in this case, I stole this from some lecture slides, so it's a movie like Harry Potter. You can substitute Harry Potter for a tank top and you'll get the idea. But it describes things like, how much do I like a lot of color? How much do I like a particular texture? How much do I like a particular manufacturer? And then the corresponding item embedding will say, to what extent does this item exhibit that particular color or that particular texture or that particular manufacturer? And then the inner product will say, well, how much are my preferences consistent with that product's properties, and therefore how likely am I to buy it? And you can think about this as kind of a matrix factorization problem, where you have this partially observed matrix matching users to items, and the entries are saying, okay, for those items that the user did purchase, how do they evaluate it? And we'd like to approximate that matrix by these low-dimensional factors, which describe the user's preferences and the item's properties. So you might get a model which looks something like this, where you've got some global offset, some user and item biases, which maybe say what's the user's activity level or the item's popularity level, and then these low-ranked factors that say how compatible is the user with the item. Okay, so this is the really important part of the model, because it's these low-ranked factors are actually what describes the user's preferences and the item's properties. And just very quickly, I'll say a few words about how we actually optimize this type of model. It's a very standard sort of supervised learning scenario where you're given some training corpus of items that the users in your data set evaluated, and you'd like to fit the terms of the model such that the predictions made by the model are most consistent with the observed ratings. Okay, so sort of standard supervised learning framework. And you can adapt this to the binary case using this model called BPR, where instead of trying to estimate a user's rating, we're trying to estimate a binary value which says did they purchase or not. So in this case, we'd take an item that they did purchase and an item that they did purchase, or click on versus not click on, and then we try to maximize the separation between those two things. We'd like to assign a higher score to the thing they did click on compared to the thing they did not click on. And that's really all I'll say about how we optimize these things in a supervised setting. In terms of actually how we incorporate fashion, all we're really doing is saying, how can we build upon this non-fashion and non-temporally aware model by updating this component of it. Okay, so this is the basic model. It's a very successful model in general, but what are some of its limitations, especially with regard to things like fashion datasets and clothing recommendation? Well, one issue is simply that it's not very effective for these obscure items or long-tail data. So like in clothing datasets where you have a continually changing vocabulary of brand new items, this is called the cold start problem. You can't really estimate these low-dimensional item factors, right? You can't say what are the reasons people evaluate an item a certain way if the item has been evaluated very few times or never been evaluated before. Another issue, of course, is that it's not temporally evolving. And the final issue is maybe that it's not interpretable. We get these anonymous vectors describing what are the properties of the item, but we don't know what those vectors mean. Ideally, we'd like to use visual signals so that those vectors would correspond to kind of interpretable fashion dimensions, and we could say, well, what kinds of fashion does this user actually like? And yeah, I'll talk about Amazon today, but this is a particular issue on other data sets we've looked at, like Tradesy, which is a clothing trading website, where you see the same users show up many, many times, but clothing items usually appear just once and you never see them again. So there's no hope of fitting this kind of model that is based on past interactions. You see an item exactly once, you have to make a prediction. All you know about it is what it looks like, so you should use visual features. Okay, so if we want to use visual features, the basic question is, could we take this model that is well established, that estimates latent user preferences towards latent item properties, and just replace this by one that uses manifest item properties, namely these very high-dimensional visual features? So would that work? Well, probably not, okay? These sort of CNN type of visual features are incredibly high-dimensional. So if you imagine trying to fit this model for each user, you'd be trying to say, what's their 4096 dimensional preference vector towards each of these visual features? Unless the user has performed thousands upon thousands upon thousands of actions, you can never possibly do this. So you have way too few observations, and more importantly than that, most of these features probably have nothing to do with what you would call fashion, right? They describe some high-level or low-level visual attribute of the image, but they're not actually the visual attributes that people consider when making purchasing decisions. Okay, so we can't do it and wouldn't want to do it anyway. What can we do this better? What we're going to try and do is learn this global item embedding, which projects these 4096 dimensional features into some much, much lower dimensional feature space that says what are the fashion relevant dimensions of this feature vector, or what are the combinations of dimensions that describe the variance in people's opinions towards products. And this is going to be a global embedding learned for everyone, which sort of says project these images into fashion space, if you like, and then we're still learning this very low dimensional preference vector for each user, which says how much do they like or dislike each of these fashion dimensions. Okay, so that's our basic model. This is something we call visual Bayesian personalized ranking. It's still not temporally aware, but I'll get to that in a minute. So basically you have this pre-trained CNN, a high dimensional visual feature that we project into a small number of dimensions, and then we combine it with some user preference vector that describes how much they care about each of those learned fashion dimensions. Okay, so I'll talk about some results from that model in a minute, but first of all I want to say, how can we extend this kind of thing to be temporally aware? Yeah, because fashions obviously change over time. Even this Amazon data set, you have purchases going back 10 to 15 years, right? So essentially what you want to do is to take this basic model we've developed and replace it by one where parameters are time dependent. So we're now indexing the probability of a purchase or a click, not just by the user and the item, but by the time they might click on something. So essentially what you might do is take each of these parameters of the model and replace them by parameters that are now a function of time. And then how you make these things a function of time is kind of the difficult modeling aspect. All right, so the first thing we might try and do is learn some very high-level global notion of how fashions change for the whole Amazon community, if you like. So we'll focus on this embedding matrix. Rather than having a single global embedding matrix, we could have an embedding matrix that changes over time. Perhaps there's a different one every year or something like that. This turns out not to work very well. This thing's reasonably high dimensional, think 4096 by 10 or something. So if you have one of these for every single month or year in your data set, you fit way too many parameters way too quickly, and you're just going to overfit. So we do this pretty simple trick. Don't worry too much about the math. It's kind of a standard idea from optimization. We essentially say, since we have way too many components to fit naively, we'll assume that these temporally evolving matrices have kind of a low rank plus a sparse component, and we can achieve sparsity through regularization. So it's a very sort of standard trick from optimization to prevent overfitting. Okay, so that's some notion of how globally fashions change over time. The other thing you'd want to capture is how individual users change over time. If you've been buying clothes on Amazon for 15 years, probably the kinds of clothes you're likely to purchase have changed. Maybe you grew up and became an adult. Maybe you're buying clothes for your children now, I don't know. But the kind of way we could model this is to say each user's preference towards each of these fashion dimensions is also going to be temporally evolving independently of this like global evolution of the Amazon fashion zeitgeist or something like that. So we kind of choose this nice trick, which is from the Netflix recommendation paper, where we fit this sort of parameterized class of functions for each user in each fashion dimension. You can take a bunch of different shapes, which essentially say for each user and for each fashion dimension, they become more attracted or less attracted or negatively attracted to that fashion dimension as time goes on. And that's just at the cost of 2 additional parameters per user. The third thing we want to model is kind of the boring thing, which is temporal effects that are simply due to the Amazon marketplace itself. Like, if you try running the model I've just described, it'll work okay, but I don't know, maybe in 2003 Amazon started selling socks or something like that. And if you just run this model, it's going to think, whatever visual feature describes socks suddenly became incredibly fashionable. But that's not fashion, right? It's just a sort of boring function of your marketplace. We should attempt to sort of control for that feature so that you can find the features that are left over which actually describe what you would consider to be fashion. So the basic idea here, and there's a lot of similar ideas that I won't go into, is just to say, well, per category we can also have some bias term that just says at a particular kind of year is this category of clothing, like winter coats, very popular, or did this particular category of items suddenly become popular at some period in this data set? And yeah, this is a non-fashion temporal dimension, of course, but you have to model these sort of high variance non-fashion dimensions so that what is left over is what you might describe as fashion. Okay, so yeah, you get this sort of Frankenstein type of model at the end of the day, which has all of these different visual and temporal and sort of Amazon dependent dimensions. And I'll very quickly skim through some results. We sort of have the basic non-visually aware model versus the visually but not temporally aware model versus the complete model that I've just described. And yeah, you get fairly substantial improvements in predictive power by adding visual features, about the same for both men's and women's clothing, but you get the largest improvements in sort of cold start settings, where you've observed very few past interactions with those particular items, which is something very important for fashion recommendation, where you have these very long-tailed data sets. And of course, you can visualize these things as well. I think you've seen probably several TS&E embeddings today. This one's a little bit different, of course, because not only do we have this embedding which describes, according to the fashion zeitgeist, which products are considered to be similar in terms of their fashion attributes, but we also get these nice heat maps, it's a bit cut off there, which essentially describe how have the fashionability of these particular items changed over time. So this is just a zoom in of some fashion style. Maybe somebody in the room can name it for me, that has apparently started out unpopular, gained in popularity, and then sort of faded away again during the lifetime of the data set. Okay, so what did I not get time to describe? First of all, how do you actually do temporal segmentation? Of course, we don't just fit one model per year or something like that, but we actually use some dynamic programming tricks to try and figure out, okay, when are the points in time where fashion was evolving very quickly or very slowly, when something actually happened in this data set. We also have some nice fine-grained visualizations. This is from our WWW paper a few months ago. And we did actually try and do some analysis of how fashion's changed according to Wikipedia or something like that, and to see if it actually jived with our model. Okay, so quickly, a few other things I'm working on. We can talk about this during whatever's left of the coffee break, but we can also adapt these models for things like outfit recommendation, to do things like predict co-purchases and find items that are compatible with each other. And we compared this to some nice ground truth. This is from a TV show called What Not to Wear, where some experts have labeled what is and is not fashionable. So we can say, how does that compare to the learned Amazon notion of what is fashionable, and measure whether people who buy all their clothes on Amazon are actually fashionable or not. And we've also been applying this to non-fashion websites. Like, this is a similar model we used for a website called Behance, which is digital art recommendation, where you also want to capture similar relationships between preferences and temporal dynamics and visual features. Okay, so I think I'll call it a day there. This is the work of a bunch of co-authors, but mainly my student, Ruining He. So hopefully there's some time left for questions. Thanks.